So in this video we're going to be taking a look at an example of a circuit which's got a capacitor, a couple of resistors and an inductor all in series with one another. I didn't write this question and it's a bit strange, but it's it's a challenge. So let's have a look. The interesting thing about it is you're not given a voltage across the circuit, you're given a current that's flowing through it which has zero phase angle at that time. So that's different, let's put it that way. So from this, also in the question it asks you to find the voltage across here and the voltage across here. Okay, which again is unusual because normally you wouldn't bother, you just go for the whole circuit and just do the whole circuit. But a question's a question, so let's have a look. So let's have a look. So Z1, so we're going to find, so XC is going to be 1 over 2 pi frequency times the capacitance value, and it's a complex number we're using as well, so that's going to be a J term. Remember, impedances such as capacitance and inductance are the imaginary part and the resistor is the real part in a complex number environment. So if I put the numbers in there, I've got, I'll just drop the J for now, so 2 pi, frequency is, I forgot to write that on there, is 2,300 hertz. So 2,300 hertz. Okay, 2.3 kilohertz. Okay, so times 2,300 times the capacitance, which is 9.489. As you can see, these are carefully chosen values by somebody. I'm just going to, because of space, I'm just going to write C in there and just write the answer, because you can do your own number crunching part of this. Apparently that gives me an answer of 7.2924. So ohms, or I tend to use R for ohms. It's a trick we do in electrical engineering really, or electronics particularly, use R instead of this symbol, just because it's hard to write from your keyboard. It's a lot easier just to put an uppercase R in. Okay, so that gives me that. So that means the impedance of Z1 is going to be, so they're out of phase, so the impedance across here, this is 44 ohms, this is 90 degrees out of phase, and remember with an inductor it actually lags, so it's going to be 90 degrees behind, but if I plotted it on a graph it'd look like this, so it'd be 44 that way, it's a terrible arrow, and 7.2 this way. Okay, so the answer to that is going to be, using Pythagoras, 44 squared plus 7.2, I'm going to shorten that to 9 squared, and that gives me an answer of 9.41. 0.41 ohms. No, it doesn't. I don't know where I got that from. That gives me 44.6. You can tell that's wrong because it's going to be greater than 44. 44.6 ohms. Okay, so that's the impedance of that part of the circuit. Okay, for Z2 then. So Z2 is to find the inductance, the reactance of the inductor. I said this was for an inductor, by the way, that would be an inductor, sorry, so this is all wrong, it would be actually the other way, up there. But it makes no difference to the maths at this stage. Sorry, I'm confusing the matters. So this is the one where it's going to be in front. lagging behind the inductor. Anyway, I move on quickly before I embarrass myself anymore. XL 2 pi frequency, the inductor value, which is millihenries. Okay, so the mass for this is, and so we've got 22, and then we've got this first. The answer to that, if I put the numbers in, I get 51.5623. I think 56 is going to be near enough. Okay. I'm just going to squeeze in here because I didn't put in the phase angle, which will come in later. The phase angle of this is found from, so the phase angle is found from the inverse of tan minus 1 of these two. So it's the, going back to my bit up here, okay, it's opposite of the adjacent, and the opposite is the lower value, which is 7. So it's 7.29 divided by the 44, and that gives me a phase angle of 9.41 degrees. Okay, so I can write that in polar form now, complex number polar form. In fact, I will up here. Z1 is 44.6. Allegedly, I say allegedly, I'll explain that in a bit, because phase angle with resistors, impedance is a bit weird. 9.41 degrees. Right. Z2, which I'm working on now, is, so this is going to be, Z2 will be square root, so this is the one that would be this is the inductor, so this would be trailing, so it goes along 22 and down 51. This is going to be quite a steep angle when we get the phase angle there, and that will give me, the Pythagoras of that is 22 squared plus 51.56 squared gives me 56.06 ohms, and the phase angle is going to be the inverse of tan of 51.56. Now this, because this is lagging, we're going to have a minus sign there. Okay. And 22, and that will give me, you can just put this into your calculator without the minus sign, and then just add the, as long as you've got a picture in your mind that it's actually lagging like that, that's your resultant, that phase angle's lagging, and you know it's going to be a fairly big phase angle as well, bigger than 45 degrees anyway. We know that that'll give us a bit of a picture, and we know from that, doing the maths, it's going to be a minus value, so we could do it without putting the minus sign in and just add it at the end if you prefer. That gives us a value of minus 894 degrees. Okay, so I can now write that over here. So I've got magnitude of 56, 0.6, phase angle minus 66.894 degrees. Okay, So I'll keep that bit of information as we move along. I definitely need a bigger whiteboard for this. Right, so I've got some comments to make about this phase angle discussion, phase angle issue. So we've found a phase angle for the impedance. So strictly speaking, impedance doesn't have a phase angle, but it's a nice mathematical convenience. It certainly causes one in the current when you put a volts across something. Again, we've got another contradiction there because we haven't got the phase angle on the current, so it's going to be the volts. It works, it's just a peculiar way of looking at it. It's not the usual way, but just keep it in mind as we move on. Now, that's assuming that we've got a phase angle for the voltage, and the only way we wouldn't get a phase angle for the voltage is if XC equaled XL. Okay, which evidently it doesn't, but if it did, they would cancel out. So if, for example, this was some resistor value, okay, that's a resistor value. If this was the same length as this, then they would cancel. So you just have the resistor, and that's the only, and it's only the inductor and the capacitance that causes a phase angle. So if they cancel one another out, then you'll have no phase angle, and that's the only way you would have voltage to have the same phase angle as the current. Okay, so that means the voltage must be out of phase with the current. Okay, that's what I'm getting at there. Right. So just keep that in mind as we move on. Just make sure there's nothing in here I should have said. I've just said everything I've written here a lot quicker. Okay, right, so that's straightforward. So, the next part of this strange question was to find out what the voltage is here and what the voltage is here. Across Z1 and across Z2. Okay, so again, a bit unusual to do it that way, because you just go and do the whole circuit, to be honest. I'm going to rub this lot off, give me some space to work in. Okay, so we're given that I equals 10 amps with a phase angle of 0. Okay, now Ohm's law says this. Okay, so the current times the impedance, and we found the impedance to be V across the resistor. So this is, we'll call this R1, call this R2. So R1 is going to be 10 times the resistor. There's 10 amps flowing through this circuit. Okay, so we've got 10 amps times 44, which gives us 440 volts. That's across the resistor. Okay, bear that in mind. And the VC, still got 10 amps going through it as well, so that's 10 times 7 point, I've rubbed off the relevant piece of information there. Good job I've got it here. 7.29. I've got it here as well, actually. 7.29. That's the impedance of the circuit, of the capacitor. Okay, that gives me 72.924 volts. Okay, thing to bear in mind though that they're 90 degrees out of phase. So if I plotted them, I'd have 440 for the resistor and 72.9. Can't really squeeze on there. So that would give me that as a resultant. So again, we're down to Pythagoras. So V1, if we call this V1, VZ1 if you prefer, Z1, is going to be, again, the usual 440 squared plus 72.924 squared, which gives me an answer of 446. You'll notice it's very symmetrical to the resistance. It's going to be, isn't it? So 446 volts. Okay, so that's across this part of the circuit, Z1. So let's have a look at the other one. Same approach, ZR2 is going to be 10 times 22. Is it 22 ohms for the R2? Gives me 220. Okay, and VL is 10 times 51.562. That was that impedance of that, and that gives me 505, if I can read my own handwriting. 105.62. Of course it is 62 volts. Okay, so that one would look something like that. You've got 22 that way and 56 that way, and it's that. Okay, and the phase angles is the same thing. If you do what, it's just what we've already done, and you'll get the same results, same phase angles, because it's the impedance that's caused the phase angle. Okay, right. So the next question on this question, which is what I said you'd do anyway in the first place, is find the total supply voltage across this circuit. So there's two ways of doing it. We can take these two results we've got here and add them together. Well, it's the volts actually we would be adding together. But you'd have to treat it as a phasor or a vector, so you would have to convert. These are basically in polar form. These are just time, you just add times them by 10 and that by 10. Convert them to rectangle form, add them together, and then you have to convert them back. Or let's just do what you would have done in the first place, which is possibly the easiest way, and that's just to treat it as one circuit. So I'm going to rub this out. Let's see what I need to keep. So VZ1 is 446 volts, and Z2 is 515.62 volts. Okay, keep a note of them. Okay. So let's have a look. So the easier way, treat it as one circuit. Two resistors in parallel, you just add them together. 44 and 22 is 66. Okay, so we've got 66, which would end up being 660 this way, but anyway, 66 if we're in volts, I mean. 66, and we've got going in this direction, the capacitor direction, which I've lost the number again, but it's on here, 7.29. Just a bit of rounding, 7.29. Okay, and this way 44.97, is it? A bit scruffy that. Lost it. Yeah, 44.6. That's what I've supposed to have written. 44.97. Yeah, 44.6. It's a lot longer actually. So that's the inductor. So that's 44.6. Okay. So because these are 90 degrees opposed to 180 degrees opposed to one another, all we do is cancel this one off this one. Okay, so we'd end up shifting this up, and we'd get, oh, I see what I've done, sorry. Right, that would actually be, yeah, I have confused myself with my scruffy handwriting. That would be 51.56. And then the resultant's going to be there like that, because you take 7.29 from that, and that's where my 44.9727, I don't know, 44, should have written the maths, 44.27. Okay, so my resultant is from them two, and that'll be my phase angle. Okay, so that will give me, so V supply going back, switching to the volts, because that's where we're heading anyway. The V supply, that's the principle of what we're doing using the impedance, but using the volts, we've got 660 volts squared, so that would be represented in the volts across the resistance, and the resultant across the capacitor and the inductance is going to be this number times 10, so that's what have I done there? I'm confusing myself again. Yeah, sorry, I get it. It's 51. It's basically 51.56 minus 7.25. I've sort of confused myself with what I've written here, but never mind. So that would be 440. No, I'll leave that. Just a correction here that I'll do. Okay, so my resultant voltage then is going to be square root of 66 squared plus 44.27 squared times 10 for the current, and that gives me an answer of 794.7 V. Okay, now the phase angle is this bit here, so that's that distance there by that, so that's going to be the inverse of tan. You'll notice in physics and maths and engineering we always end up using these two common things, Pythagoras theorem and basic trigonometry, particularly the inverse of tan. It comes up so many times. Now this is a negative. I didn't put a negative in there, but it's a negative. Okay, so that would make that minus 44.27 divided by 66 gives me a phase angle of minus 33.85. I can just about squeeze that in. Remove that there. Okay, so my resultant, and I'll put this over here, so the V total, V supply, is 794.7. Let's do it in polar form. With a phase angle of minus 33.85. Okay, degrees, and that's all in volts. So that's my final supply. To be honest with you, you just do that right at the beginning. Actually, you wouldn't do all this finding the individual ones, but it's a good exercise. It gives you a bit of understanding what's going on and how all those phases interact with one another and change things. Okay, so the volts is lagging the current by minus 33, or you could argue the current is actually leading the volts, which is the more usual argument actually, is leading the volts by 33.85 degrees. Okay, right, so that's mainly that done. The next question on the thing was do a vector diagram, and depends what you're looking at with the vector diagram. I'm going to rub that lot off. So if within volts, so what have we got here? We've got it's mainly got 660 volts. We've got 72.9. Obviously, if you're doing this on paper, doing it on graph paper is not a bad idea, but do it to scale anyway. And we've got down here something like this. It's probably too far. It's probably around here. We've got 515. 515? Yeah, 515.6. Okay, so you subtract that from there and you're going to get a value here. That's going to be our resultant. Okay, so that's a minus. That's a minus 443. So that would be resultant there. So if you're doing a vector diagram, do something like that. So in actual fact, we've got, doing this in different colours. I've only got really two colours available, my black's running out. I've got this one. So that would be, is that V1 and V2? V1. That one's V1 resultant. Then I've got V2, and then we've actually got we've got voltage supply across there, resultant voltage supply. Okay, which is that one. Like that, like thus. Okay, so that's a very scruffy version of the vector diagram. It gives you an idea what it's going to look like. Okay, and I think I've covered all the peculiarities of that question. Definitely different. Okay, so I hope that's answered everything. Any questions, post them in the comments below, and I'll have a look at them, see what we can do with them. And if I need to make any clarifications on things, I will, by all means. Okay, thank you for listening.